Our last lesson with surface area. Let's do this lesson 4, pyramids and cones today. Last shapes to talk about. Don't mind the bell. All right, we're gonna start with pyramids. Pyramids are, definition, it's a polyhedron with a base, one base, not two, like prisms and cylinders. It's got one base that can be any polygon, any shape, and all the other faces, we're gonna call them the lateral faces. Feels similar to prisms, maybe. The lateral faces are triangles in a pyramid. They were rectangles in prisms and in a cylinder. So some similarities, but that's kind of what separates them. Just one base, every other face is a triangle. So if I look at my pyramid here, you name pyramids by their bases, you guys. This one, the base is the bottom, that red face it's sitting on, so that's the base. It's a square, so I would name this a square pyramid. FYI, let's draw the net. I always start by drawing the bottom. Everything else, so it's a square on bottom, everything else is a triangle, and it like unfolds kind of like that. There's one off of each edge of your base. Not perfect, but there it is. So there's my net. Let's label a few other parts of this pyramid here. Your triangular lateral faces, they all fold up and they meet at a point at the top. That point is called the vertex of your pyramid. And then the only other thing I need to point out to you is there's like kind of like two heights in pyramids and in cones. One of them I'm gonna call the true height. So it starts at the vertex and it goes straight down perpendicular to the base. That is called the height. Sometimes, I won't call it this, but like if you ever see it, them say the altitude, I don't like that, but that's the height. They'll call that H. That's like the true height, how tall this pyramid is. To calculate surface area though, we need something called the slant height, and I'll show you why. The slant height starts at the vertex, and it's exactly what it sounds like. It's a slanted height. So it's gonna look something like that. Slant height. They don't use S, I don't know why, but they use cursive L. That means slant height. The reason we need that, if you kind of drew it over here, that's L. That is like the height of just one of those triangular faces. I don't know if you can see that, but like there's the triangle. That's the height of just that 2D face. It's like perpendicular to that edge right there. So if I'm thinking like, oh, let me calculate the lateral area is just the area of those 4 triangles on this pyramid, or the area of like all the triangles going around this thing. So here's where the formula comes from. This is like the briefest explanation I could give you, but lateral area is just like, okay, area of those triangles. The area of a triangle is half base times height. So that's where the half comes from. The height of that triangle is the slant height, L. And instead of me just going base times height, they do the perimeter of the base, because that accounts for all 4 of the triangles, or however many there are. So again, that's like kind of a crap explanation. It's just like me accounting for time. But it was like with prisms, like instead of doing the like every single one, we just did the perimeter, and that like accounts for all of them. Works out that way here as well. So that's the formula for lateral area. Maybe make a note. P is perimeter of the base. Cursive L is a slant height. That's lateral area. Get that in your notes, good. Surface area. Take the lateral area. That's all half PL is. You take those triangular faces and you want to include the base when you talk about full surface area. So you're going to tack on the area of the base. And I just have to say big B here. It says base. I have to say big B here because the base can change. Like in this first example, it's a hexagon. So I can't just give you a formula for B. You have to think about, well, how do I find the area of a hexagon? It's constantly changing. That kind of stinks. All right, maybe we'll highlight those. So first example here is, again, the bottom is, the base is a hexagon. So to classify it, I would call this a hexagonal. It comes to a point at the top. This is not a prism, it's a pyramid. I want to find full surface area. My advice, especially when all these shapes get thrown together, find your shape, write down your formula, plug in what you need, find what you don't have. You have everything on this one, which is kind of nice. So half times, okay, P is perimeter of the base, so perimeter of the bottom. Each side is 6, there's 6 sides. You also have the slant height. See that there? That's what 9 is. That's slanted height, not the true height, slanted. To find big B, that's the area of the base. It's a hexagon. You're going to have to do 1/2 AP. But this is like the best 1/2 AP example ever because, look, they gave you the apothem. That's what 3 radical 3 is pointing to. And, oh, we know the perimeter of the hexagon is just 6 times 6 again. So, oh my gosh, that's super convenient. See if you can follow my calculator work here. So half times 36 times 9 plus big B. I'm just going to plug it in as it looks right there. 3 square root, we'll do multiplied to make people happy, times 3 square root 3. I close the parentheses and then times by 36. So rounded to the nearest tenth. Didn't have to worry about simplest radical. 255.5 square inches. Fun stuff, you guys. Okay, example 2, composite figures. We saw these last lesson, and this is what bumps us up to like high school geometry surface area problems. Composite figures are 2 figures in one. The first thing you should do is identify what shapes am I looking at. This is like a diamond looking thing to me, 3D diamond. If you can't tell, it's a square pyramid on top, it's a square pyramid on bottom. When you have composite figures and it's surface area, you have to think, and I know this is the hardest part, but think, if I had this figure in front of me, could I touch every surface? You could not. The square bases connect. They would like cover themselves up. You would only be able to touch like the triangular surfaces here. You would not be able to reach those squares. They cover each other up. So all you want is the lateral area only of these 2 pyramids. So I'm going to find the lateral area of just one, and then I'm just going to double it. Okay, so half perimeter of the base. That's this square piece in the middle, what it's sitting on. Every edge is 4, so 4 times 4. Ooh, the slant height. They're giving you the height here. That's 3. The slant height is going to look like this. Like it's going to look like the edge there of your face. If you are ever missing the slant height or the height, you use Pythagorean theorem. I don't know if you can see that nice little right triangle there. Down here, this whole thing is 4, so that's half of it, 2. Slant height is always the hypotenuse, so I would just solve that, do Pythagorean theorem. It's a square root of 13, so it's about 3.6, but I don't want to round it. I'm just going to take that here. But when I calculate this, I'm just going to use that running decimal. Okay, 28.8. That's the lateral area of just one pyramid. There are 2, top and bottom, so I'm going to double that. That's my answer, 57.7 meters squared. And you guys, I get it that is tough. Again, that's what separates this stuff from like middle school surface area volume problems. All right, let's shift gears and end with cones. This is the last shape that you'll have to find surface area for. Okay, cone is really similar to a pyramid, except the base is always a circle. It's not changing, always a circle on bottom, comes to a point at the top. These are a little bit better than pyramids. Okay, let's label the base. I think we all would see that. Let's draw the net. So the net of a cone, if you kind of like unraveled this thing, I think we would see, oh, it's a circle on bottom. The lateral, like smooth face, I always think of a snow cone. I don't know if you know what a snow cone wrapper looks like, but it's triangular, but it's more like this, like that. And then there's that circle base. Looks a little awkward, but that would be the net. To find the lateral area. So this is gonna feel similar to pyramids, but there's two parts, we'll label them here too. There's heights and slant heights in cones as well. So like that's the height. Call that H. The slant height is just gonna look like the edge of your cone when you draw it two-dimensionally. Still gonna use cursive L for that. Okay, so slant height, and again, if I just think, oh, lateral area, that's just the area of this triangular face right here. And it's kind of triangular in nature, so we do still say like, oh, half base times height. Now, the height of it is gonna be the slant height. This is kind of a stretch and a crap explanation for a 15-minute video, I know. The base of it is actually the circumference of the circle. Ooh, that's kind of deep for too many of us, but the length of this is just the length of all the way around the circle, which that's circumference. So this is the formula. You don't have to know where it comes from, just how to use it. But watch, I'm gonna simplify this. Half of 2 is just 1. That cancels out. So call your lateral area formula just pi RL. If you even want to erase that one, go for it. Pi RL is what I'm going to look at. R is the radius. L is the slant height. Full surface area. Take your lateral area, pi RL, what we just wrote, that's LA, and you tack on the base. The area of the base, I'm not going to do big B because it's always a circle. I'm going to do pi r squared. Okay, let's maybe highlight those, just like we've done the front. Those are the big things that I need to know. All right, 2 examples. Number 1, I want to find the surface area in terms of pi. And I'm just going to plug in right from here, guys. This is pretty straightforward. Pi r, radius would be 3. Pi RL, that's the slant height, plus pi r squared. What I want to show you here is the in terms of pi part, okay? Here, you don't want to put pi in your calculator. So what I do is I figure out, well, how many pi's are here? 3 times 8, there's 24 pi's right there. 3 squared, that's 9. So there's 9 pi's right here. You can add those together. Those are like terms. Shouldn't need a calculator for it. There's 33 pi's here. I'm making some of us hungry. That's your surface area. So kind of just to show you like the in terms of pi with that can kind of be weird. I could have just plugged it into my calculator without pi, but we like to do things the hard way. All right, real life example. This is a good one to end on. Funnel below is being used to make snow cones at the baseball games. How much paper do you need to make each funnel? Okay, application problem. Just like the lint roller thing or the soup can label, you have to think, do we put paper on the entire cone? No, we do not cover the top of the cone with paper. Otherwise, you wouldn't be able to put the snow cone stuff in there, the ice. So I only need paper on the label. So it's lateral area only. Okay, so that's pi RL. Here's the picture. So the radius would be 4. To get the slant height, you always use Pythagorean theorem. So look for your triangle. I want you guys to finish this one. See if you could do Pythagorean theorem to get the slant height here, and then take that value and plug it in. And you're gonna round your answer to the nearest 10th. And that's our last surface area lesson.